Alright, hello everybody! Hello, hello, hello. Welcome back to Math 126. Ladies and gentlemen, hopefully you're doing absolutely fantastic. Yes, it's Gemma! How we doing? How we win? How we doing? It's almost mini. Hey, oh, Khadija back for his second go around. Mercy. What am I supposed to say to that? Sophros! Backman, hey, thanks for the thumbs up. Long time no hear, my dude. We doing alright for a midnight go? Very good. I can respect that. What do you mean it's 12 p.m.? It's 12 p.m.? Well, it's 6 hours behind, 6 hours ahead, 6 hours wherever. I just know it's 6 o'clock right now, p.m. We're all good and we're all good here in this corner of Twitch. It's 1 a.m. in Germany. I respect that. There you go, Sulfros. Just doing the homework. Decided pop by, say hello again. Hey, I appreciate it. You're always welcome here anytime, Khadija. 1000%. You want to pop in at any point in time? I do not mind. We're here to just chill, hang out, have a little fun, have a little math, and have a fantastic time. I might just sit through this just to see how hard it is. I mean, you can, absolutely. Gemma wants me to say something nice. Oh well. Well, this time I got. Why not? I don't see a problem with that. 500 channel points. It's easy, right? I'm gonna lower the volume for this. Just a smidge. Gemma. I'm gonna look straight at the camera here. Gemma, you are a national treasure. You should value yourself much more highly. There will be a guy out there who will absolutely value based on the value of what that treasure is, which I value to be very high. You bring radiance into any room you walk into, and I'm sure that if everything goes to plan and you are a successful actress, you'll bring radiance into every person's TV or monitor. I can guarantee that. Believe in yourself, believe in the dream, and you will go very far. Gemma, we love you, respect you, and you're an absolutely outstanding person. Never forget that. There you go. Might I say something nice? Did you hear about the Japanese math riddle? I did not. What's the Japanese math riddle? What's that? I haven't heard. Hopefully, Gemma, I hope you like that. That was straight from the heart. That's legit. Okay. Now that makes me smile. Can you translate can I translate a website? I can. Water time. Nick says water time. Water time. Only if you tell me what oh, crud. Okay, hang on. I got to give you a moderator again. So pros. Give me a sec. Let me I got to make you mod again. Like I remember I made you mod before. How do I make you a mod again? I've made you a mod before. Okay, someday I'm gonna have to figure out how to make a mod. Oh. I'm like derping out about how to make a mod. Bad. Ah. Okay. Here we go. And there we go. All right. There. Now I made you a mod. Perfect. All right. Now you're a mod, Sofros. There you go. I had to get the right link there. It's weird. You can't mod through Streamlabs. You can mod only through the. This was my plan all along. I see how it is. I see how it is. Try again. Try the link now. You have to repost the link because the first time Nightbot would have censored the link. So now if you try again, you should be able to get it. All right, there we go. Wait, I just see. You have to. Oh, Nick, you did do hydrate. Okay, I'm sorry, bro. Yeah, 100%. There you go, buddy. There you go, buddy. Thank you for the hydrate. Thank you. Let's translate this to English. Let's take a look at this one here. Let's go. There you go. Let's go. Let's go. Let's do this problem. Oh, I like this problem. This one's pretty good. So 9 minus 3 divided by 1/3 plus 1. Okay. 9 minus 3 divided by 1/3 plus 1. Okay, I know the answer to this. Alright. Yep. This one is really easy. What do you guys think? If you look at that, right? 9 minus 3 divided by 1/3 plus 1. I'm very curious actually now of what people think what that is. But why it went viral if it's so easy? It's easy for me because I know exactly how to do it. It's a common thing that I actually teach when I actually do basic arithmetic. Order of operations is definitely a thing. It's kind of tantamount to saying if you've ever done the classic problem of like, for example, I do this one, for example. This is what I show in like basic arithmetic class. I do 6 divided by 2 times 3. And then I ask everybody, okay, tell me what the answer to this problem is. Right? And I'm only ever going to get 1 or 2 answers for this problem. Why don't you guys tell me, what's the answer to this problem? And it's going to work very similar to what the top problem is. Six divided by 2 times 3. What do you guys think that is? Like, legit. Should we do a little poll? You guys want to do a mini poll? I can do a mini poll here. 42? Haha. Sorry, my friend. That's the meaning of life. Not quite in this space. Elizabeth says 1. They are only gonna get 2 answers, right? Is it 1 or 9? I agree. I agree. I'll put up a poll here. Small poll. The answer to this is 1 or 9. One of those two is correct. You guys gotta pick the one that's correct. So put up a poll there on the top. Think it's 1 or you think it's 9? I'm gonna go with 1 because multiplication comes before division in PEMDAS, okay? Lamau. This one here actually gets a lot of people just because of PEMDAS itself. So all right, so 5 people said 1, 1 person said 9. Okay, I'll tell you the correct answer here. The correct answer to 6 divided by 2 times 3 is going to be 9. That is the correct answer. The answer to this is 9. Now, let me go ahead and point out why that's the case. Yes, of course. Why is that the case? Right? Now, as you all are aware of is PEMDAS. You guys are very well aware of PEMDAS. But the way PEMDAS is actually shown is incorrect. The way PEMDAS should be shown is exactly what I have up here on the screen. In basic arithmetic, the way it specifically works here is that m M and D, multiply and divide, you actually do on the same rank. Multiply and divide are the same rank. There's no difference on how you would do it. So if you look at add and subtract, right? If I looked at add and subtract, I did 6 minus 2 plus 3. You would be like, okay, just go left to right and just do 6 minus 2 plus 3 and you'd get 7, right? No, you're not. That's what you're doing, right? You go left to right. So my point is that why don't you do the same thing with divide and multiply? There are no parentheses here in this case, so they're the same exact rank. Yes, use parentheses as often as you can in programming to make the computer be absolutely sure that you want that operation done first. But multiply does not come before divide in an order of operations because of the ranking system that actually occurs. It is the same exact rank. When you put parentheses there, that means you put priority in that particular expression. With no parentheses, you're going to assume multiply and divide are the same rank. In this problem here, 9 minus 3 divided by a third plus 1, you do 3 divided by a third first, which is going to be 9. And so you do that, you do 9 minus 9, 0 plus 1, that's 1. So that's what you get for that one there, for that problem. So it always comes down to priority. But M and D, multiply, divide, just because multiply comes before divide doesn't mean that multiply is always done before division. So I always tell people, like, if you have 6 minus 2 plus 3, don't you do subtraction first and then add and subtract all the way down? Like, why don't you do the same thing with multiply, divide? Why are you changing the rules all of a sudden? Why you gotta be like that? What? Why does your 5th grade teacher have to lie to you like that? It's a very fascinating problem, but yeah, it's just one of those things that, one of the things about order of operations that I have to actually deprogram people out of, in all honesty, when I teach basic arithmetic, is I get this answer all the time. All the time. I'm like, you can't, you're not doing it that way, no. So, like, please, help me out, please. Do me a solid. There's also order operation and logic operations, correct, right? And it depends on the language, absolutely correct, right? So if you're talking logic operations like if and you're talking about nors and ors and, if and only ifs and nots, yeah, there's definitely an order of operations for that. So yes, I completely agree. All right, that was a nice way to start the class, I guess. Good way to start. I can't really argue with that. All right, ladies and gentlemen, let's go ahead and get started here with class. We gotta get started here. Thank you for that math riddle, dude. That was really. Sophros, you're always welcome here in this course. Anytime, my friend. Anytime. I'm glad you're doing really well. It's good to talk with you again, man. We'll tell you the right solution here. Oh my goodness, this is so. 9 is just wrong, of course. It's B1. Yeah, exactly. All right. Okay. All right. So today, ladies and gentlemen, I want to point out a couple of things here before we get started for today. Before we get through the intros. Actually, let me do the intro. Let me do the intro and then we'll get started. All right, let's do this intro. Let's get going. No, still got the right clap. Nope, still not. There we go. Better. Okay, let's get started today. Welcome back to Thursday, end of the week time today. End of the week time today. Thank you, Sophros. I really appreciate it. So today, ladies and gentlemen, we're gonna hopefully finish up the last couple of sections here of Chapter 5. If you haven't checked out the homework yet, I have today actually just posted the practice test and the actual test for the Chapter 4 and 5 exam. So that is now posted and done and dusted. All right, so it is up there. I pared it down to 50 questions. And again, the practice test is now up there, and the real test is up there for you to go ahead and peruse and attempt. Okay, so that is there for you. Okay, so just make sure you get that done and, get that thing going. All right. Okay, so, all right, so, but we're not quite done with Chapter 5. We're almost there. We just got a few things we need to talk about here. And today we're going to be talking about our good friend Natural Log. Natural Log is going to be our buddy today. A lot of buddies. Natural Log. All right, so let's discuss Natural Log. Let's see exactly what we're working with here. And then we'll do a lot of derivatives with natural logs because it can be a little tough. All right. So let's go with question number 1 here on the handout. Question 1. What is the derivative of natural log? So natural log is going to be its own unique guy. Natural log, the derivative of natural log, if you take the natural log of a function, is going to be the derivative of that function over that specific function. Or if you looked at it from a very super basic perspective here, super basic perspective is the natural log of x. If you took the derivative of that, the derivative of natural log of x is equal to 1 over x. 1 being the derivative of x, and the original value of x that you're taking the natural log of. Okay, so this is going to involve a lot of chain rule stuff and whatnot. A lot of this stuff is going to just be kind of down the line when it comes to things like that. So all those concepts we talked about here, again, tangent lines and all, find the derivatives stuff using the chain rule, all that's going to be applicable here when we're going ahead and putting together certain problems. Now, of course, we need to take a look at what these certain problems are, and let's go ahead and work them out together. Okay, so a lot of today is going to be those examples that we see there in the homework. So let's look at each of them here respectively, and let's see if we can get comfortable. I don't think it's a bad thing. Okay, let's look at the first one here, number 1. Okay. Oh, let me switch over here. Sorry. Put that up one more time there. Guys gotta remind me when my camera doesn't shift over. Alright. Hopefully you can grab a, I'll actually, let me give you a minute to write that down. I meant to put this up to start with. All right. Okay, you guys ready? Let me know if you guys are ready. Just go ahead and say if you're ready in chat there, and then I'll go ahead and get started. Apologies about that. I meant to switch my camera over. Nick, Elizabeth, Lee-Wen, Emma, yes? Okay. All right. You ready? Okay. Perfect. All right. Good stuff. Okay. So let's do the first one there. We have the natural log of 6x. Okay. So if we use the rule here, again, we're going to use the chain rule to find out what the natural log of 6x is. So basically, you take it into 2 parts. Imagine if this was your function f, right? Again, doing the derivative of natural log of any random function. Again, you're just going to have the derivative over that function. All right, so Anybody tell me here, what's the derivative of 6x? What's the derivative of 6x? 6. Correct. So we're going to have 6 over 6x. And then we just simplify this. This becomes 1. This cancels out. Leaves us 1 over x. So the natural log of 6x is exactly 1 over x. That's it. That's all you got to do for that one. That was pretty fast. Let's try number 2. Natural log of 4x plus 5. All right. All we're going to have is something over its original function of 4x plus 5. What's the derivative of 4x plus 5? What's that derivative? Four? Okay. And that's it. That's the derivative of the natural log of 4x plus 5. 4 over 4x plus 5. Yeah. Let's look at the next one. Five natural log of t to the 5th. Yep. All right. Okay. So again, in this particular instance, although the 5 is on the outside there, yes, so you just need to be a little bit careful about that. That 5 on the outside there is going to be, remains out there. It's just going to be hanging out there in the numerator. Yeah, you got the extra 5. Extra 5 out there. The rest of it, though, as you've put out there, Elizabeth, is correct. So that will be the 5t to the 4th over t to the 5th. Okay, so that part is correct, okay? Again, that's the derivative of the natural log of t to the 5th. So you can play around with this a little bit. Again, you get rid of 4 t's, you end up with 1 t left over. And so here you get 25 over t as your final answer. Okay. All right. We got a few tricky ones to look at now. Now, those are the easy ones, okay? Those are the easy ones. Now, we got some other tricky ones to do, though, and it may not be as simple to look at. All right. Let's go ahead and take a look here at number 6. Probably saying, man, these are so simple. Be like, yeah, I suppose that's fair. Let's erase these, and let's go to number 6. Okay, now we have the natural log of x plus 3 over x minus 3. Now what we need to do is, to follow the rule, we need f prime of x over f of x. Okay, that's the natural log here. However, let's go ahead and try and find out the derivative of this inside function here. Okay, so if we're going to find the derivative of this inside function, again, let's use we are forced to use the quotient rule in this instance. We have f and g. Again, we have f prime g minus g prime f over g squared. All right. And so again, what's nice about this is that f prime here is 1 and g prime here is also 1. Again, the derivative of x is just 1. So let's follow suit with what we have. We have 1 times g, which is x minus 3, minus g prime, which is 1, times f, which is x plus 3, over g squared, which is x minus 3 squared. Okay. Now we need to clean this up a bit, so let's clean this up just a smidge. So we have x minus 3 on the top. We have minus, I'm going to distribute this minus to both of these. So we have minus x minus 3. So we're going to go ahead and cancel out an x. So on the top here, we're left with negative 6 over x minus 3 squared. Remember, this is the derivative of the inside function, okay? This is what we have here so far. So if I were to do the derivative of this, on the top here, I would put all this junk. Minus 6 over x minus 3 squared. Then we're going to put this all over, so we got all this thing over the original function of x plus 3 over x minus 3. Okay. I'm going to stop here for just a second, make sure that everybody can see how I came up with that. Any questions about this particular, at this juncture here, about how I at least came up with this part? There's a little bit more simplifying to do, but just making sure everybody knows where I'm coming from on this. So far, so good? Okay. All right. I understand? Perfect. All right. Good, good. All right. Now, next. What we're going to do next here is going ahead and simplifying this. Now, when you divide by a fraction, remember that you flip that bottom fraction. So what we have here is minus 6 x minus 3 quantity squared, and you can basically rewrite this as times, and you flip this bottom fraction, so you have x minus 3 over x plus 3. And that happens anytime you divide by a fraction. So you can cancel out one of the x minus 3's, and you're just left with your final answer here, minus 6 over x minus 3, x plus 3. You have that last little bit of simplification here. That'll be your final result there. Excuse me. So we check it out, and that is correct. Okay. All right. Questions about that? Okay. Well, I'm going to give you guys an option, of course. Once again, the next example here can be between 7, 8, or 9. Okay, so 7, 8, or 9. For the next example here, which one would you like me to do? Between 7, 8, or 9? You guys pick them. Pick that next example, and I will do. All right, 9 it is. Okay. Let's go ahead and do number 9. And let's see what we're working with, okay? Still, we're going to try and find the derivative of this next one here. So for number 9, we have g of t equals t squared times the natural log of e to the 2t plus 3. Okay, so this one here is basically what we're going to be doing is we're going to be doing the product rule on this particular function in order to find the derivative. So this is going to be our f, and this natural log here is going to be our g. So again, if we're going to do the product rule here, remember that's f prime g plus g prime f. Okay, so we know how we're going to apply that. Now we're just going to go ahead and find out these derivatives. So the derivative of f here, the derivative of t squared is easy. That's just 2t. So that part there, not hard at all. Okay, let's talk about g though, and talk about the derivative of the natural log of e to the 2t plus 3. So one thing that you do have, and one thing that you do have to the bank, you know, keep in the bank here, is that this is going to be over e to the 2t plus 3. Okay, just using the rule for natural logs. We need to find the derivative of e to the 2t plus 3. That's what we need to find. Now, the derivative here, I'm just going to focus on this here, and then I'll put the derivative up here. E to the 2t, the derivative of that is going to, again, use the chain rule in order to find that derivative. So we did this last time here with e functions. So in this instance, we keep the e to the 2t the same, and then take the derivative of 2t. Again, the outside is the e to the x part, or again, e to that power, and then taking the derivative of that power, which is 2. Right, so what we have here specifically is we have 2e to the 2t. And again, the plus 3 here drops out because any derivative of any constant number is automatically 0. So that one just kind of drops out for that derivative. All right. That is the derivative of g prime. So that again, notice I just kind of picked it apart one piece at a time. Okay. And now we can go ahead and do the product rule using this f prime and g prime and this f and g, and see what we get. We get f prime g, so we get t squared times g, which is the natural log of, oh, I'm sorry, f prime should be 2t. My apologies. F prime t. So 2t natural log of e to the 2t plus 3. That's f prime g plus g prime f, so plus g prime, which is 2e to the 2t over e to the 2t plus 3, and then times f, which is times t squared. You could put the t squared in front of the 2, or next to the 2 if you wanted to. That would be just fine. And then that's it. That's all you need. This is the derivative here of this particular function. So let's put it down. See if we got it. So get 2t natural log of technically e to the 2t plus 3. Okay, plus 2t squared. Again, I just moved the t squared in front of next to the 2 there. Nothing fancy going on there. And all this is over e to the 2t plus 3. Okay, and that is going to be our answer for this particular problem. Let's check it out to see if this is right. And as you can see there, that is correct. All right, good stuff. Any questions about that? guys a second here to write stuff down. So. Nope. Hopefully that now made sense. Just putting those pieces together one at a time, okay? That's essentially what we're doing, okay? No fancy tricks, no hidden messages, just putting one piece at a time, one foot in front of the other, and we get it, no problem. All right. Now, the next one I want to do here is going to be, let's see, let's do number 11 here as our next example. And this one here is a little bit different than that of other problems. Now, admittingly, numbers 10 and 11 can be done in the same vein as just doing regular differentiation. However, in number 10 and 11, they would like you to use logarithmic differentiation to find that same result. So the question is, how would you go about doing that here in this instance? Okay, let's take a look at how that would happen. And again, as I mentioned here, it doesn't change anything, okay, in terms of how would you do this out. So it does pretty much the same thing here. Now, let me check, actually. I'm going to check one thing here in actuality. I think I have to do that, but I better make sure extra. But I'll write down number 11 regardless. Because the first part of the process here is exactly the same. So number 11 here, y is equal to the square root of 3x plus 5 times 2x minus 9 to the 4. Okay. Again, what you can do is rewrite this problem here one more time. Again, square root can be rewritten as 3x plus 5 to the positive 1/2 power. Get 2x minus 9 here to the 4th power. Okay, so that part there by itself, not too hard. Okay. All right. Now, let's have to be sure about one part here. Right? Da, 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 da. Okay, that's all they want. Okay, that's fine then. All right, I don't have to do the extra step. All right. Good, good, good. All right. Okay, so the next thing that we're going to do here is basically we're going to take the derivative of this function here. Now, in order for us to do that here, what we want to do is we want to take the natural log of both sides, okay? So at this stage, you don't have the natural log. So again, you want y prime to be on one side. You want the other stuff to be on the other side. Sure, one more time. I gotta be double extra sure. Not going banana-ramas. That's already set up that way. I don't want pre-set up problem. Okay. Okay, that's all right. Okay, so we're going to take the natural log of both sides here. So we're going to take that's kind of the key here that we're going to do. So let's. All right, now if we take the natural log of both sides here specifically, let's see what we get here in this instance. We're going to get natural log of y equals the natural log of this whole shebang, 3x plus 5 to the 1/2 times 2x minus 9 to the 4th. Now, essentially what we're going to be doing is we're going to make this problem, we're going to break this problem down even further. Now, if you remember what we discussed here last time about logarithms, those log properties that we talked about before are going to make an appearance here in a problem like this to make the problem significantly easier. Okay, so as you can see here, we have natural log of 3x plus 5 to the 1/2 times 2x minus 9 to the 4th. In effect, we have two things that are multiplied by each other here. So what we can do is we can use the product rule here and break this down into two separate natural logs. All right, this is just using the product rule here in this instance. Use plus natural log of 2x minus 9 to the 4th. We can get away with that. Again, product rule is okay for this, okay? I don't have you shouldn't have a problem here using the product rule. Okay, so this is the product rule. I'm going to talk about this left-hand side here in just a moment. I will be doing that here momentarily. But I'm just right now just rewriting the problem here a couple of times. Another thing I can do here is that I can use the power rule. Again, this 1/2 and this 4. Okay, why bother working with that here with the chain rule, which could be more complicated, when I can just automatically use the power rule, just bring it out in front. So I could have 1/2 natural log of 3x plus 5 plus 4 natural log of 2x minus 9. Okay, so that's what we have here to start with. Not too hard, very straightforward, okay? Easy enough. Okay, so up to this point here, it's not too hard. Just went ahead and did a few things here that were pretty easy from what we learned about from before. Now comes the part here where you have to be very careful. Okay, so at this stage of the game, just rewritten it. We haven't done the actual derivative yet. So now it's actual derivative time. Now, admittedly, the right-hand side isn't too hard to do now that we know what the rule is for natural log. It's actually pretty straightforward. The part that you have to be careful about, though, is that left-hand side. That's natural log of y. Now, what do you get here for the natural log of y? Now, this is what you get here for the natural log of y. You get y prime, which is the derivative of y, divided by y. And it's still using the log property, the derivative rule here for derivatives, just using it with y instead of x. Okay. And so, if you recall here, we are going to solve for y prime. Okay, this will be important in just a second. Solve for y prime. Let's find the derivative of on this right-hand side. So the derivative here, we have 1/2 times 3x plus 5 here on the bottom, and the derivative of 3x plus 5 is 3. Have that. Plus 4, and then we have 2x minus 9 here on the bottom. We have a 2 here on the top. Alright, so if we have that so far here, this is what we got. Alright, you can clean this up a little bit if you like. But I'm going to do, actually, let's clean that up a little bit, actually, now that I think about it. Let's do 3 over 2 times 3x plus 5. I know I could distribute here, but I'll just leave it like that. Plus 4 times 2 is 8 over 2x minus 9. And I got this y prime over y here on the left-hand side. Okay. Now comes the most important part as part of the process. That left-hand side is going to play a big role into our final answer. Why? Because as it says here, I'm trying to solve for y prime. Now the only way I'm going to solve for y prime is by doing one thing. And that is I need to multiply by y on both sides. I'm going to multiply this whole thing by y. So why is this important? Well, because we already have defined y here as our original function. So now at this stage here, note, substitute the original function. That y is equal to. Okay, so our final answer here, underneath this logarithmic differentiation, is everything you see there in the brackets. Okay, so I'm not going to change that. Everything in the brackets. And then I'm going to multiply by y, which is this original function we have here. I'm going to multiply it by 3x plus 5 to the 1/2 and 2x minus 9 to the 4th. And this is going to be our final answer for our problem. Okay, so we did that last little bit of substitution, and we got this as our answer for this particular problem. So let's enter this in and see if this indeed is our correct answer. So let's do it. Alright, so I'm just kind of showing this off here. Put a bracket here. E times 3x. I have 8. Brackets are closed, and then here we'll have 3x plus 5. Raise that to the 1/2 power. Multiply that by 2x minus 9. That to the 4th power, just like so. Okay, let's check our answer here. And as you can see, that is correct. Okay. Any questions about that? So hopefully that wasn't too bad. Again, there's just a lot of some moving parts there. I won't disagree, but again, just getting it down isn't as bad as it may seem. One piece at a time, everybody. Always one piece at a time. Okay. All right, if there are no more questions, I'm going to go ahead and move forward. On paper, I get it, but it is a lot of parts to remember. It's true. But if you notice how we've done all our derivatives here, Nick, has always been one piece at a time. Okay? Everything we've done has been always one piece at a time. I want to find the derivative of natural log. Okay, use the rule, right? It's f prime over f. Derivative of this inside function here is 3 over 3x plus 5. Did the same thing here for 4 natural log of 2x minus 9. Okay, apply the same rule, just doing it one at a time. So if you need to, just go slow, okay? You don't have to go a million miles an hour, and notice I did not go a million miles an hour with this question. So real slow like. If you need to, rewatch this video again. Guarantee you, it's pretty much how I've been kind of doing these type of problems here. They get ugly and nasty very quick, so it's like, okay, let's take it one at a time. Okay, let's try the next one here. We're going to do there's a specific problem I want to do amongst these three. That is, I want to do number 13. So 13 is going to be the next problem that I would like to do here. So let's go over that one here specifically and see how we can get that out, right? Okay. I'm going to go ahead and erase this one, and we'll go to 13. Alrighty. Okay. So 13 here says marginal revenue. The demand function for a certain boat company is P is equal to 900 minus 0.01x times the natural log of x, where x denotes the number of yachts and P is the price per yacht in hundreds of dollars. Alright, so letter A says find the revenue function and the marginal revenue function R prime of x for this model of yacht. So they first want us to find out what R of x is. Now, this will give us a friendly reminder is that, remember, the revenue function here specifically is price times x, the number of units that we sell here, in this case, this yacht. All right? So we're going to take that p function that it gives us here, and we're just going to straight up multiply by x, okay? We're not doing anything fancy. It is what it is, and that's all it really. So I'm going to multiply this by x. Now, when you multiply by x here, just to let you know, what are you going to get here? You're going to get 900x minus, and this x here is going to pretty much distribute over to this x here. Not with the x on the inside of the natural log, it'll be this x here that's outside. So 0.01x squared, and then a natural log of x is what we get here. Okay, so let's at least write that in first. Okay, so that's going to be our revenue function. We can check that first and foremost, and you'll see what we have here. Okay, so you notice the first part here is correct. Okay, we got the revenue function here working out exactly as intended. Now the next half of this particular part is to find the derivative. Okay, so the derivative we just need to be careful about here once again. The first half of the derivative is very easy. That's going to be just straight up 900. Derivative of 900x is just 900. Fine. The next part, though, you will need to use the product rule on this second half. So just be a little bit careful with this minus sign also in the front. So I'm just going to separate that out, and we're just going to do that very carefully here. We're going to 0.01x squared, natural log of x. So again, you can label this your f, you can label this your g. Let's go ahead and just do, again, product rule f prime g plus g prime f. So f prime here is equal to, have x squared here, so we bring out the 2. Do 2 times 0.01 x to the first power. So this equals 0.02 x. Next we have g. The derivative of natural log of x is just 1 over x. Okay, so just using our basic rule for natural log. And now all we want to do here is go ahead and start putting the pieces together. So we put f prime g. So 0.02 natural log of x. Okay, and 0.02, oh, I'm sorry, I did that wrong. 0.02x natural log of x. 0.02x natural log of x, I forgot that extra x. And then plus g prime f, so 1 over x times prime f, so 0.01 x squared. Okay, so if we clean this up a little bit, let's clean this up. I'll expand on this actually. Easier to see. So here we get 0.02x natural log of x. One of these x's cancel, so that's fine. Plus 0.01 x. Okay. So we have minus, and then this whole expression here, minus 0.02x natural log of x plus 0.01x. Okay. So let's enter that in to the derivative. $900 minus brackets plus see if that's correct there. And that is correct. Okay, so we got both the actual revenue function and the marginal revenue function, which is just its derivative here. Okay, so before we move any further here, are there any questions about that? Feel free to ask before we move on to part B. Okay, no questions so far from Liwen. Emma? Okay, so no. Elizabeth, Nick? What's your, what do you guys think? Get it? Alright. I think you're okay so far. Alright. Now get ready for part B. Oh, you're gonna hate me for part B. Alright. Get ready for the hate train, everybody. Part B. Alrighty. Ladies and gentlemen. Part B is gonna be one of those things. One of those things, okay? Part B asks, using the result of Part A to estimate the revenue to be realized from the sale of the 475th 34-foot Sundancer yacht. Round your answer to the nearest dollar. Okay. Now this is actually really confusing if you don't know what you're doing. Okay. Now you're gonna be like, okay, what the heck is going on here? If you want to realize the amount of revenue you want to realize from the sale of the 475th yacht that you sell, you actually are not going to use the revenue function here. In fact, you're going to use the marginal revenue function here. Okay, so I want to point out you're going to use R prime of x. On top of that, you're not going to be using 475. Okay, although we want to recognize here the rate of change after X amount of yachts are sold. In this case here, I would like you to go ahead and use X is equal to 1 below 475. You're actually going to use 474. Okay, so you're going to first use R prime of X, and then you're going to go ahead and use 474 to represent the first 474 yachts that you sell, okay, which will reflect the realization of revenue from the next yacht you sell. So we're actually doing R prime of 474 here. All right. I'm just being as specific as possible. Regardless of whatever numbers that they give you, you're just going to go one less than that number, okay? I just want to point that out here, okay? Now, as we see here for R prime, you're going to plug in 474 in for this. So you're probably looking at this like, oh my gosh, this looks pretty terrible. I'm be like, yeah, I guess that's kind of fair. So let's go ahead and plug this into a calculator though, and then we'll see exactly what value that we get here in this particular instance. Okay, so I'll show you how to do this on the calculator, because it's kind of a rough go if you're not careful enough. I'm gonna take this one a little slow here for entering it in. So. Bring the calculator over. All right, so to do this one appropriately, I'm just going to have this R prime of x up, and we want to enter in 474 for x in both cases, all three cases, I should say. I'm going to have 900 minus, and then the quantity here, I'm going to go ahead and put in parentheses, 0.02 times 474. I'm going to take the natural log, and then you notice you'll have parentheses next to that, 474. Close off those parentheses, plus 0.01 times 474. And then close the parentheses off from the first set of parentheses. Can't really put brackets here. You can technically, but it's more of a pain to do. All right. Want to be sure that everybody got that. Is there any questions about that? About how you enter that into the calculator there? And let's take a look at what we get here. No? Okay. All right. So here we get, let's see, what do we get here? We get 836.85. 17546. Blah, 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 blah. All right. Now, we're not quite done with it just yet. You're probably saying, we did all that work and we're not quite done yet. I'd be like, yeah, not quite there just yet. Now, why is that the case? Well, one of the things in this problem that you need to be very careful about is the wording in this problem. It's very deceptive because the number that we get here, the price that we want to find is in terms of hundreds of dollars. Okay, not just singular dollars, like this is not $836, it's in hundreds of dollars. So specifically here, we get 836.851. So basically, we are going to take that number and multiply it by 100 to reflect hundreds of dollars. Okay? So we're going to take 836.851, we'll multiply that by 100, and so we're going to get $83,685.10, or just $83,685 is what we'll get. So you could just multiply this by 100 next, and then that's essentially what you're going to end up with as your final answer. So $83,685 will be the final answer for the problem. So let's check it out. And there you go. That is the correct answer. Okay. Questions? Questions about that final example here from this section? Okay. So the next question is, again, we're at about 7:06 here, so would you guys like to take a break or keep going? All right, so Lee Wen says keep going. I shall hear from the others to see what they have to say, and then we'll just roll with that. Let's knock it out. Almost done for the week. Okay. All right. Fair enough. Let's keep going. All right. If that's what the majority says, that's what I'm going to follow. Full send, he says. Full send. All right. That's fine by me. Full send. All right. I'm not selling Nelk merch, okay? But we'll full send anyway. Just saying. All right. Anyway, let's go ahead and do number 3. All right, from the handout. Again, number 3 here is reflective of the section 5.6. All right, so let's go ahead and do number 3 here. Number 3, what is the general form for exponential growth and decay? So the last section here deals with exponential growth or decay. And the way it works is fairly simple here. It says A equals A0 e to the kt power. Now we've dealt with E already significantly in this chapter, so once again, I'm going to be dealing with E when it comes to growth and decay. Now these growth and decay problems all revolve around basically constant K. So if you take a look here, A0 is the initial amount, how much you start with. A is the ending amount. K is the constant of growth or decay, so how fast is it degrading, how fast is it growing. And T is time, and time here is dependent on context, whether that be minutes or years or whatever the case may be. But one thing that we could take to the bank here is that if K is bigger than 0, that's indicative of growth. If k is less than 0, that's indicative of decay. Okay, so again, we have expectations. If we're having a word problem here and it says, oh, you know, your money is growing, okay, then your k should be positive. Okay, or again, a particular element is decaying over a long period of time, well, then that k should be negative. Okay, so something to that effect is really what the expectation should be. So we're going to be doing number 4. I didn't actually put an answer here for number 4 because, well, there's a lot of different ways to do growth and decay models and problems like that. So just going to do straight up some word problems. I'm just going to see how it works. Okay, let's do it. How do I still have this on? All right. Okay, so let's take a look here at number 1. We'll start off simple, and then we'll just work our way forward. I don't think that's such a bad thing. And I fully expect us to get through this today, so that'll be the end of chapter 5 after this. Okay, so number 1, exponential growth. Given that the quantity q of t is described by the exponential growth function of 500 e to the 0.01 t, where t is measured in minutes, answer the following questions. What is the growth constant k? So if we follow the generic model, again, a is equal to a0 e to the kt power. In this case here, the k is again in your exponent of e. So again, k here is going to be 0.01. Okay, that's going to be our constant k, in this case, our growth constant. If you want to know what k is in actuality in terms of like a practical use to kind of make sense of, k being 0.01 would represent a 1% growth, okay? K is a decimal, convert it to a percentage, 0.01 is 1%, so a 1% growth, if you want to put it in practical terms. What quantity is present initially? Well, you guys can answer this. What's the initial quantity here in this instance? What's the initial amount according to this equation? $500. Okay, good. That's it. That's all you need to put in. 500. Simple enough. All right. That's it. Okay. And then the rest of these are basically just plug and chug the numbers in for t. So if t is 0, what would you get? You would get 500. If you plugged in 10, you just plug it into a calculator. So I can show you here via the calculator. You do 500 second and ln to get the e, 0.01 times 10, then close parentheses. So 552.585, or how many decimal places you want. A nearest integer, so 553. Okay, so whatever. All right, and that's it. So yeah, that's pretty much it. Okay, I'm not gonna go through every single painstaking problem. That would be take quite a while to do. All right. Let us take a look here at some other problems, though, of where this is going to be, again, practical problems where we can actually apply these. There are not many problems here, by the way. There are only 7 problems for this section, just to let you know. I know a few of you will be like, yay! Only 7 problems. Okay, that's fair. All right. Let's do number 3. Number 3 says world population. The world population at the beginning of 1990 was 5.3 billion. Assume that the population continues to grow at a rate of approximately 2% per year and find the function q of t that expresses the world population in billions as a function of time t in years with t equaling 0 corresponding to the beginning of 1990. Okay, and so it asks us a couple questions here. If the world population continues to grow at approximately 2% per year, find the length time t required for the population to double in size. And using t of 0 found in part A, what would be the world population if the growth rate were reduced 1.7% per year? Okay. So let's take a good look here at this one. So the first thing that they want us to do is to set up the problem here appropriately. Now, in order for us to do that here, first have to look at the initial amount. The initial amount here is 5.3 billion. So we're just going to put 5.3 for the sake of use. We're not actually going to put 5 billion, 300 million. That would be ridiculous. So to set up this problem here, we have A is equal to 5.3. That's our initial amount. E, and we're also given a K here. One thing I mentioned here before is the practicality of what K is. Remember, K here, we have a growth rate of 2% per year. That means our K here is going to be 0.02. So we're going to have 0.02t. Okay? So just initially setting up this problem, this is what we have here so far. Okay. Questions about that? Again, setting up this problem here is probably the most important part. The rest of these aren't as bad, but it's all about the setup of the problem. This is easy? Excellent. All right. Now, let me show you how it'll be done here. Let's look at here. We got if the world population continues to grow at 2% per year. Find the length of time for the population to double in size. So if it says double, what should the population be if it's double? So we started at 5.3 billion. What should double the population be then? $10.6 billion, that's correct. In this case here, specifically, A needs to be 10.6, okay? So if we set up this problem here, this is what we should have. Taking our original model, 10.6 here should equal 5.3 e to the 0.02t. All right? And all we're going to do here specifically is go ahead and solve for t using our log properties and the whole 9 yards. There's not even derivatives to do in this, so just log properties, really. So divide by 5.3. Here we're going to get 2 is equal to e to the 0.02t. To solve for t, we're going to use the same trick we used last class. Take the natural log of both sides. Take the natural log of both sides. This natural log and e will cancel each other out. Get natural log of 2 is equal to 0.02t. And then divide by 0.02. How many? 2 decimal places. So let's use our calculator to solve for t. Have natural log of 2 divided by, so 34.66 years. Okay, if we're going to 2 decimal places like they asked. Okay. All right, so let's check that. So we got that correct. 34.66. All right, easy time, easy life. All right. So it says here, using time t0 found in part A, what would be the world population if the growth rate were reduced to 1.7% per year? Well, all that it's asking us to do for part B is really, really easy. It's just asking us, hey, can you just change 0.02 to 1.7%? Can you go ahead and do that and just plop in the numbers? That would be great. That's all they're asking us to do for the second part. So there's no super complicated thing. We'll start off with the same 5.3. We just changed K here. Instead of 0.02 to reflect 2%, we're going to have 0.017 to reflect 1.7%. And we'll multiply that straight up by 34.66, the answer we got from the previous part. So let's go ahead and put that in the calculator, see what we get. The 5.3 second in natural log. Actually, I'll clear the screen here. 5.3 second natural log, parentheses, 0.017 times 34.66. We get 9.55. So let's check it out. And that is correct. Okay. Easy peasy lemon squeezy. So far, so good. Alrighty. Okay. Questions so far? Sounds like you guys are having an easy time of this. Hopefully. Question mark. Okay. Nick, do you have a large pina colada in your hand? Sipping it based on how easy it is? I mean, if that's what your emote is, then hopefully you're doing the same thing. Because it's just that simple. Question mark. It's water, but yes. That's fair. Emma, you okay? Emma, any questions? Actually, I have some water right now. Good? Alright. Alright. Alright, so let's do the next one. Do I drink that whole gallon every day? No, of course not. No, this is the same water I've had for like a week. So I try and drink other things other than the gallon of water. Like, holy smokes, drink a whole gallon of water, man. I'm about to be mind blown. In fact, I think my bladder would be blown before my mind would be blown if I drank a gallon of water every day. we would have lots of problems. Okay, I'm just gonna point that out there. am I gonna have to stop class at least, 3 times while I hit the restroom? Alright, it's like if you go to the bar, okay? Same deal. Oh, At the bar, you gotta go to the restroom a few times. That's just how it is. So, alcohol dehydrates you, so you're like, I gotta go take a leak. Like, okay. Drinking a few more beers, I gotta go take a leak. Alright. Um, ay, ay, ay. Alright. Okay, let's take a look here at the next one. Okay. What is this? Number 4? Number 4. Alright, let's do number 4. Number 4, radioactive decay. So phosphorus P32 has a half-life of 14.2 days. If 200 grams of the substance are present initially, find the amount Q of T present after T days. Okay. So in this case here, we have a half-life. Now, first of all, we have to describe what half-life means. All right, so just a quick synopsis here of half-life. Not the game, but the actual term. So half-life here is going to be the amount of time it takes for something to become half of its original mass. Okay? That is a half-life, the amount of time it takes for something to become half of its original mass. All right, so if we follow that here, we actually have initially we have 200 grams of this substance here. But then after 14.2 days, that gets cut in half. Okay, that's just what happens. It gets cut in half. All right, so what we can take to the bank here is to set up this problem here appropriately. Is we have the initial value of 200. What we don't know is the rate of decay, because we know it's going to decay here, but we don't know how fast it's going to decay. All right. So the way we go ahead and say we have K here, but what we do know is that after 14.2 days, that's going to cut in half. So this is going to equal its respective counterpart of half of 200, which is 100. And then we just solve for K here first and foremost. So we'll divide by 200. So we're going to get 1/2 here on the left-hand side, e to the 14.2k. And we're just going to repeat the same process we just did for the previous one. Just it's like take the natural log of both sides and solve for k. Let's do it. Natural log and e will cancel out just as normal. Okay, so we're going to divide by 14.2. And so let's go ahead and figure that out here. They may require, here they require 4 decimal places. Actually, yeah, 4 decimal places what they'll require here. So that's what we're trying to do is this first part here, because we need the K part here to find out how much is left over. So let's go ahead and figure out that out here. Natural log of 5 by 4. So going out to 4 decimal places, we have negative 0.0488. Okay. So our equation that we're going to be using here for the remainder of this problem is going to be 200 e to the negative 0.0488 d. That's what we'll have here to start with. And then basically it says, okay, well, how much is it going to, what is the amount in grams that will be left after 19.2 days? Well, that's pretty simple. In this case, we're just going to plug in for part B. This will be part A. Part B here is just, okay, hey, this is our function. Fine, that's great. Plug in 19.2 into our original function. See what we get. Right. So let's see what we get here. Oh. Calculator. So we get 200 second natural log, parentheses, negative 0.0488 times 19.2. And get 78.363. 3 decimal places, yeah. So 78.363. Sorry. Now, the last part here is you need to be very careful about. Last part here says how fast in grams per day is this particular thing decaying when t is equal to 19.2. So the key thing that you have to be careful about here is how fast. And since it says how fast, we need to go ahead and take the derivative of our original function. Okay, so in this case here, we do need to use the derivative here. So we're going to go ahead and find that out right now for part C. Let's find out what q prime of t is. And that's just doing a pretty simple job here. Again, we keep everything else the same. All right. Get the same stuff here as we started off with, just we take the derivative of the exponent, which is just times that negative 0.0488. And all you're going to do here, you can multiply it now or you don't really have to. Plug in your 19.2 here. Then you'll be good to the GTG to go. Let's put this in the calculator. Let's see what we get. We get 200 e to the minus, I need parentheses first, sorry. Parentheses minus, not that minus key. Let's try this again. Minus, right, gotta use the negative key. 0.0488 times 19.2 in exponent. That right key again, thank you. Times negative 0.0488. And then let's see what we get. And so here we get negative 3.824. All right. So we have 3 decimal places here, so negative 3.824 grams per day. Let's check this out here. Oh, actually we don't need the negative here. I think we just have the positive here because it already, the reason why we leave off the negative here, just to let you know, is because it already says decaying. So decaying means you're already losing something. So I think they just want the positive result. Let's check it out. Yes, okay, that's what they're looking for. All right. And that is the answer for that question. Questions about that one? right? Okay, so let's focus on the last example here for today. That will be number 6. That will be pretty much the end of section 5.5, or 5.6, pardon me. Let's look at number 6 here. Number 6 is probably one of the most common things that you do with exponential growth and decay is carbon date. So if you want to know how old something is, you can do carbon dating on that particular object and find out how old that object is. So carbon-14 dating. So skeletal remains had lost 76% of carbon-14 that they originally contained. Determine the approximate age in years of the bones. Assume the half-life of carbon-14 is 5,730 years. Round your answer to the nearest whole number. Okay. Now in this case here, we're going to do pretty much something similar that we did to the last problem. We need to solve for k first, and then we can go back and try it again. So it gives us the half-life here of 5,730 years. So with that, again, we can basically make one assumption here. You can assume as much as you want here. Essentially, assume an initial amount. All right, probably the easiest initial amount you can choose is you can choose 10 or 100. I think people mostly like 100 because it's easy. So just assume an initial amount. Hopefully. There. Just assume an initial amount. So let's say that equals 100. A0 equals 100, for example. Like I said, you could use 10, you could use 100, you could use 1,000. Usually a nice, simple, flat number people really like a lot. So in this case, if we assume that there's 100 grams of carbon or whatever, we do know that it takes 5,730 years to go ahead and cut in half. So we know that at the end of the day, there should be 50 grams left after that amount of time. 50 pounds or whatever you want to call it. So we go ahead and solve for k here first. And divide by 100. You'll notice we're getting the same things that we just did in the last problem. So this part here is pretty much like, okay, nothing crazy going on here. Take the natural log of both sides, okay? Nothing too crazy. You're like, okay, same dealio. Everything is the same. We're solving k the way we want it. Okay, fine. Now, after I do this is when things will start to change a little bit. Everything's been up to this point pretty much the same. Now let's do this on the calculator here, and I do want to talk about one thing here at this juncture. So we have the natural log of 1/2 divided by 5730. Okay, so that's what we have. Okay, so I'm just going to point this out here. This is going to be our k. Now, this k here is negative 1.20968,094. This e to the minus 4 here is reflective of times 10 to the negative 4th. So let me go ahead and show you what that means. That way you don't mistake this for the wrong number. Yeah. This e is times 10 to the minus 4th. That's this blocky letter e, and minus 4 is equivalent to times 10 to the negative 4th. So the real number that you have here, if you have something, say, times 10 to the negative 4th, you're going to move that decimal point over to the left 4 places. You're going to have 0.1230 120968094. Okay. So So this will be your K value to reflect the half-life of carbon-14. Also notice, I will point this out here as a note, a very important one in this case. Do not round, okay? Do not round. Unless the problem asks you to round, then go ahead. But if the problem doesn't ask you to round, don't round. Keep it like this. It's a long decimal, yes, but it has to be done in this. So let's look at the next part here then. So we have our equation here. We have A is equal to A0 e to the, it's K here. Okay, now let's look at what's next. What's next is to figure out how old the bones are. In this case, the skeletal remains had lost 76%. Okay, so they lost 76%. Be very mindful of that, by the way. That's the tricky part here in this problem. That they lost 76% of its original mass. So if we make the assumption here that we started off with 100 grams or pounds of carbon-14, okay, how much is left over now? So if we lost 76%, how much is left? If we started with, let's say, 100 grams, how many grams are left if we lost 76%? How many grams are left if we started with the... So if we lost 76%, how many grams are left? Initial. And that's the biggest question here. We're going to get this question correct, then we just have to ask, if we lost 76%, how much is left over? See if you guys can get this here. 24. Okay, good. So that's the tricky part about this problem. We lost 76%, so by default, we actually have 24 of these grams, or whatever unit you want to use, left over. That's correct. 24%, yes. So now let's solve for T. We're going to do it exactly the same way here as we just solved for K. Nothing too crazy going on here. Let's do it. Let's finish this problem off, and then this section here is effectively done and dusted. Take the natural log of both sides. Hello? Hang on a second. Alright. So we'll have natural log of 0.24 minus 0.002096894, sorry. Divide by this thing. I'll just put a little I want to write that again on that side. Alright, let's put it in the calculator. Alright, 0.24 divided by negative 0.000120,968,94. So T here is going to be equal to 11,797 years old, approximately. So, unless they want it rounded up, I don't know. So I'm just gonna take a guess here if they want this one or they want the 8. They want us to round up. So let's check out the first answer, 797. If that's what they want us. Let's see if that's their answer for this one. So yeah, okay, so they want the 797. They just run it rounded to whatever. So, all right, and that is number 6. So just had to do the problem 2 times here, but it really wasn't as bad as it may seem. All right, good. Any questions, anybody? That effectively is the end of Chapter 5. That's it. That is Chapter 5 in a nutshell. We got through 2 solid sections here today. So lots of stuff accomplished here today. We're in good shape. So, oh. Alrighty. Okay, ladies and gentlemen, thank you. Thank you very much for sticking around here for the full time. I would like to make a very small note here, just for you guys here for this weekend. Again, we are not meeting on Monday, okay? So we are not meeting on Monday due to 4th of July weekend, okay? Okay, so we are not meeting Monday for 4th of July weekend. So we will be back here on Tuesday, okay? So Tuesday is the next time we are going to meet, all right? So that's July the 5th. Also on July the 5th specifically is by July the 5th, I have to enter in midterm grades. Now, of course, everybody's kind of doing their own thing on the, in terms of like the work and the tests and whatnot. So basically, I'm just going to be taking a look at your homework and your tests there. I'm just going to be looking at a general overview. I'll give you all like A's and B's and stuff on your midterms. Okay, so it'll show up on your midterms there, but again, there's no midterm for this class. It's all tests and homework anyway. So pretty much that's basically all I'm going to really do. All the grading will be done at the end of the semester anyway. So since everything is due at the end of the semester, so that is that. But I have to put in a midterm grade of some variety. So I'm just letting you know ahead of time to expect that before on the 5th, actually on the 5th. So that's when they're due. All right. So I wanted to give those 2 little notes there, so you have you know exactly what is going on my end. The chapter 4 and 5 test is due on the last day of class, Emma, just like the chapters 1 and just like the chapters 2 and 3 test. So again, chapter 2 and 3 due at the end of the semester. Chapters 4 and 5 due at the end of the semester. The only thing that I did here today, Emma, was I just posted the test here with the practice test, of course, here today. So I remember, I think you guys asked me, hey, no, that's fine. No, I'm still holding service the same way that I did the first test. Okay, so everything is the same. I made double extra sure. All the settings were the same. Everything's the same. You have the practice test there. Okay, so same questions. Okay, and then we have the real test. You get 5 attempts for the real test. You get unlimited attempts for the practically unlimited attempts for the practice test. And again, everything should be above board, just like you had for the chapter 2 and 3 test. Okay, so made sure I was working on it all afternoon, making sure that everything was perfect for you guys before I remotely posted it. And now it should be ready for you guys to go ahead and do. And now that we finally finished chapter 5, we now again, if you're working through the homework here, kind of keeping pace, then finish up your chapter 4 and 5 homework, and then give the next test a try. Okay. And soon I'll be making up the last regular test and then the finals. That is, that's the goal. Next time, ladies and gentlemen, next time we're going to be doing Chapter 6. We're going to be doing integration. Okay? Integration is what's next, all right? All right? So I'm just going to point that out here. Integration is what's next. Hopefully you guys enjoy. All right. Thank you very much, everybody, for coming on out here today. You guys know exactly where to find me. Again, email me with questions, or again, come on Discord if you have any questions. I'll be more than happy to help you out, okay? Everybody's always welcome, all right? All right. Thank you very much, everybody. Have yourself a very wonderful evening, okay? And we will be back here on Tuesday, okay? Tuesday is the next time we're going to meet here. So everyone have yourself a wonderful, long, extra long 4-day weekend, 4th of July. Enjoy the fireworks. Enjoy the barbecue. All right? Take care of yourselves, everybody. And we will see you all then on the 5th, all right? And as always, everybody, stay safe, stay healthy. But most importantly, everybody, stay sane. All right? Have yourself a great one, and we'll see y'all later. Take care, everyone. All right. Bye. Bye, everybody.